Hello, my name is Julie Kim. This is my recording of my project. The project title is Implementation of LRU Replacement Policy for Cache Memory using FPGA. The agenda is going to be a little bit of background of the replacement policy for cache memory and proposed replacement policy. This is my proposal, and I'm going to show all the algorithm for the replacement policy and HDL coding and simulation result and the analysis summary. So a little bit of the background. The replacement policy is, this one is used in the event of when there is a cache miss, and then so the replacement policy is used in the event of the cache miss, and then for the project I'm going to use and it is also used in the 8-way associative LRU, and it is used to improve the memory access time. There are other replacement policies such as the FIFO, first in first out, or LFU, and last in first out. And there was some research in the past that saying the LRU has the highest hit rate, and especially in the event of having the 8-way set associated the set associative cache, that improved the memory access time. And with the LRU replacement policy, it also improved the memory access time. So LRU replacement policy is one of the way that is preferred to improve the memory access time. There are two type of the LRU replacement policy for my proposal, which is the conventional LRU replacement policy, and the other one is the pseudo LRU replacement policy. For the first one, conventional LRU replacement policy. For this one, as is in my design, in the design that is represented by the research paper, saying that the tag it has the array for the tag and array, the data cache array, and also the LRU array. And for the conventional LRU array policy, it has there are two-dimensional array. So there are 456 lines, and for each line, it contains another 4-bit of the 4-bit array, and the size is 8. So for one is 4 bits, so 8 index, it add up to 32 bit, 4 times 8. So that means for the LRU array, for the conventional, it take up a huge memory space. And this is the way that the replacement policy is implemented. So the list index, which is index 0, it contains the it contains the list use way. So that means if I need to find out in the replacement which way I need to use, I have to go and find and look at the content at index 0. And once that index is used, then it is moved to the most significant, to the last index, which is index 7. So let's say if the cache hit at index 1. At this index, it's not 1, actually it's this is the index 0, and then it just move up. So that means it will move it up to the last index, which is index 7, and then the next one will be moving downward. So this is another example. If this one is the the list recently used, and this one is replaced. So that means this way, the content of the index represent the way number of the set. So the way number, let's say this is way number 2, so it will move up to the content of index 7, and then the content of index 7 will be moved down, and it repeat just like this, will go down, and then whatever one that is used, it will be moved up to the last index. So this is how the replacement policy work. And then the next slide would be, this is, so in this design, I have, this is a little small, but I have the memory array, which is huge, it's like 2G, and then I have all the memory initialization. I have the address, which is 28-bit address, and the line is 250 million line of the addresses. So each, I just initialize some of the memory addresses, just use those addresses to do my simulation, to find the set, and then the set to find the to calculate to get the cache line, and then store my value into the into my cache line. This is the tree-based pseudo replacement policy, and this one, it has, for compared to the array policy, to the conventional array policy, this is way small. It also the 2-dimensional line, but one index of the 8 index, which is only 1 bit, compared to the conventional one index, there are 4 bit right here, so total is 32 bit, but for this one, it is only 1 bit each. So that means for the total array of 4095 line of the tree-based pseudo LRU replacement policy, it takes up only 48 times. One line is only 8-bit compared to 32-bit. And this is how the replacement policy for so for initial start of my program, I will start by having initialize the cache line and the data line and the tag, and then once it hit, then I will get the data from the cache. But if it miss, then I will retrieve the data from the main memory, which is 256 million lines of memory. Each is 128-bit, and this is how the algorithm for the conventional algorithm work. One is so just like I explained earlier. Okay, stop that. So this is how the conventional LRU algorithm work. The algorithm, it works based on the LRU array that's shown earlier in this page, this array. So initially, which is a 32-bit of array for each line, and this is the array that I initialize at first. And when the cache hit, the algorithm check for the value at index 0 of this array, and then the content of the array represent the least recently used way, and to replace the cache way is to use the way number of index 0. So go to the number of index 0, grab the content of it, and that will be the least way used to do the cache replacement policy. And the next slide will show the algorithm, which is an HDL code, how to find the least recently used way. And the slide after that will show the algorithm update currently used way to be the last access way of each line of the 4095 data cache line. Basically every time when any set is when any way of any set is accessed, the LRU algorithm will update the way to be the currently used way to be the last way in the set that is used, and move down whatever the way move downward, just like this diagram. If this one is accessed, this one is moved up to the last index, and then the other way is moving down toward the index 0. So this is how the algorithm works. I have this way, this one and this one, to find the how to find the least recently used way in the set, and this one is it update all the time every time the any way in the set is used. And then this is the tree-based pseudo LRU algorithm, and this one is just so the array size is like smaller. It has the same line, but each bit it is just one bit, and it has only 7 the array need only 7 bit. Yeah, it's only needs 7 bit in compared to the conventional LRU. It needs 4 times 8 is 32. So if look into here, so this one, this is an 8-way set of tree-based pseudo LRU replacement policy, and then it needs 7 bits. 1, 2, 3, 4, 5, 6, 7. If it is 4-way, it needs only 3 bits. So that means the bit number to represent or to store the LRU is the number of the way minus 1. This is 4-way, need 3 bits. 4 minus 1 is 3. This is 8-way, need 7 bits. 8 minus 1 is 3. So this is how the algorithm works. The middle bit is the one that decide which side is going to be used, which side is going to do the replacement. If it is at reset initially, I initialize the way way 0 is the way that need to be replaced. So initially in my array, I have the value at bit 3 as 1, and the value of bit 1 as 1, and the value of bit 0 as 1. So 3 is 1, bit 1 is 1, bit 0 is 1. So that means initially, if I need to store the value in my cache, then it will have to go to way 0, because I set it the way that this algorithm will find way 0. So let's say if I set bit 1 is 1, that means it will go to the other way. So it will go to this way, and then go to bit 1 and check what is the value of bit 1. My value, I set it to 1, so that means it will go to the other way. It will go to this way. So now bit 0, I set bit 0 to 1, so that means it will go the opposite way. So we will go this way, so that means way 0 is selected. So one way is selected, my controller will update the way will update my array according to the way that is selected. So at reset, I have bit 3 is 1, bit 1 is 1, bit 0 is 1. And then I set my, I store my value in way 0, that so that way 0 is the current way used, and then my controller, the pseudo LRU controller, will update this array based on the way number. Previously, before way 0 was used, it was way 1. So now, since way 0 is used to store the data in the cache, so the array is updated to be 0. Bit 3 is 0, bit 1 is 0, bit 0 is 0. So that means way 0 is the one that is the one that is just used. So that means if the next time need to find the LRU, that means the algorithm will try to get away from the one that is just used, which is way 0. So that means next time, if it see bit 3 is 0, then it will look to the other way, to the 1, and then it will check on bit 5, will check on bit 4, and will check on bit 6. So this is how the algorithm work. I would just want to clarify a little bit more. So if bit so I just want to clarify a little bit more. If bit 3, so now is way 0 is the one that just used. So that means next time, if it try to find the to find a place to replace the cache line, then it will go to the other way. So now my array will store bit 3 as 0. So the next time it will go to this way and look for bit 3. If bit 5, if bit 5 is 0, it will go to bit 6. If bit 6 is 0, it will go to bit 1, and it will go to way 7. So the main concept of this algorithm is that it always go to the opposite side. If the last way that is used is on one side, and it will try to do the replacement policy on the other side. So if 0 is used, then 7 will be replaced. Yeah, something like that. So this is the algorithm that I use, and this is the controller that I use. This is the main memory that I use to control the to initialize my cache, and this is the line, the initialization of my cache data line, and this is how I retrieve the memory data, whether to choose the memory data or to choose the cache data. And this is my test bench, and this is the simulation result. I have the cache I have the cache that store the data, and the tag number, and the way number, and also the LRU array policy. For the simulation result, it is it shows that the pseudo LRU algorithm, it takes a little longer than the conventional algorithm, and this is obvious, and this should be because the pseudo LRU simulation array is less than the conventional LRU conventional array, so it takes less time. And it is also true that for the hardware side perspective, if you have a huge array and a big huge arrays, it takes up space, and with the register running through, clocking data and taking data from one place to another, usually with the big size of the register will take up time for to get the result. That's why the conventional LRU, it take longer time than the pseudo LRU. But one good thing about the tree-based LRU, it is quite complex to design, but the complexity is only in combo logic. It doesn't really make any negative impact on the hardware. And also, so those two slides, it really show that the it takes up space, and it takes up a lot of logic, and quite complex compared to the conventional LRU. And then if you look at the conventional LRU on this side, the coding is really simple. It's not that difficult to design, but it takes up a lot of space, and the control is also just a couple of lines. Then it can accomplish the result. This is my simple simulation result of the LRU. After I load the data in, I do some of the memory hit. So that means I go to the same address, but then I kind of replace, move around the logic, move around the data, move around the data line, which one need to be accessed first, which one need to be accessed last. So on this column, the data are in order previously, and on this column, the data is like I take the line 4 first, and then whatever 3, and then 2, 7, 5, 6, so that when it go to the LRU control, then once it get the data from that way of the sets of set 5, 11, then it would just update the data based on the time that it is accessed. So that means the currently used will move to the top, to the last index, and then it will move whatever it is, go down to the lower index. So in this way, it says that since 4 is the first one that call, that hit, so eventually it will go to index 0, and the 1 is the last one that is used, so that is accessed. So that means eventually it will go to the top one. That's all for my presentation. Thank you.